A 15-gram bullet strikes and becomes embedded in a 1.1 kilogram block of wood on a horizontal surface just in front of a gun. If the coefficient of kinetic friction, that means friction when the object's actually in motion, as opposed to static friction, which is when it's just sitting there. If the coefficient is 0.25 and the impact moves the block a distance of 9.5 meters before it comes to rest, what was the initial speed of the bullet? Like all these other momentum energy problems, we just draw a picture of the before and after. So the before, in this case, you've got a bullet. He's pretty angry. We don't know his velocity. And he's running into a block of wood that's just sitting there. And then at the end, the bullet goes into the block of wood, and it slides some distance and comes to a stop and has no velocity. Now, you know this isn't going to be a momentum problem because, check it out. At the beginning, the bullet has a bunch of momentum on the left side, but at the end, there's no momentum left. So the momentum was sort of lost. It really went into the vibration of stuff in the floor and kind of heating everything up. But energy is really going to be our friend here. Energy is going to pull us through. And since the solution we're looking for is on this side of the problem, we must begin our attack on the right side of the problem. So we're going to use an energy argument. And that argument is work. The idea that work is how much energy was lost, and that's equal to force times distance. Now, the agent behind that energy being lost was the force of friction. And the force of friction is mu times the normal force, which is just 0.25. And the normal force is equal to Fg in this case because the object is in balance. The forces are in balance in the y direction. So Fg is 9.8 times 1.15. And the normal force is the same. So the total force of friction is 2.8 newtons. And we simply multiply that by the distance it was pushed, which is 9.5 meters. And we see that the object lost 26.7 joules of energy in the process of sliding along the floor. We use that number and throw it back at the front and say that has to be how much energy there was at the beginning. And at the beginning, all of the energy was supplied through the kinetic energy of this bullet. The Ke up here made up everything. Which means the total energy is just 1/2 mass of the bullet times v squared. And we toss those values in, solve for v, and we get 59 meters per second. Pretty quick. It's about 120 miles an hour. Okay, before we begin this next one, I gotta warn you, it's a doozy. This is probably more mathematically involved than any other problem we'll do for the rest of the year. There's a lot going on. So let's jump into it. So we got 0.45 kilogram puck moving east with a speed of 3, has a collision head-on with a 0.9 kilogram puck initially just sitting there. And if it's an elastic collision, which means energy is conserved, what will be the speed and direction of each object after they hit? Like always, we use a picture of the situation at the start and the situation at the end. That's how energy and momentum problems are always going to work. So at the beginning, you got this thing going with 3 and that one chilling. And then at the end, we really honestly have no clue what the velocity of either one is. And since we have two things that we don't know, we're going to need two equations in order to solve it. So for the momentum at the beginning, I add up all the mv's and get 1.35. And for the ke at the beginning, I add up all the 1/2 mv squareds and I get 2.07. So that's how much momentum and energy we have to work with. And that amount can't change, which means the amount of momentum at the beginning equals all of the mv's at the end, and the amount of energy at the beginning equals all the 1/2 mv squareds at the end. So I just expressed those two as my system of two equations to find these unknowns. Now in physics, substitution is usually the method of choice for solving a system of equations. So I'm going to get this v1 by itself so I can substitute it into the other equation. And that's what I do down here in red. I get the v1 by itself. You can check this algebraically. I get v1 equals 3 minus 2v2. So what I do next is I toss all this junk into the second equation so that I can solve the system. So if I scoot this over, the substitution takes place right over here, where everywhere there was a v1, I simply replaced it with what v1 is. And then you do FOIL, and then you solve the thing by using the quadratic formula. And I get two results for v2. It's either equal to 0 or 2.0. Well, the second puck obviously didn't just sit there, so I reject this answer and keep this one. Plug it into the second equation, and you get... After I plug v2 in over to the left, I get this.